Okay, hello and welcome. Just anyone who is connected, please give a thumbs up if the audio is fine because I'm having kind of problems with that. Um, right now, we are going to implement the 6522, which is also often referred to, wrong datasheet, as the versatile interface adapter or VIA or whatever. Um, it's a very interesting device, actually. The idea is that it interfaces between the CPU and whatever peripherals you want to use, and it translates the language that the CPU understands, which is a data bus and address bus, into a variety of interfaces that can be connected to the 6522. So it can be a GPIO. Let me just pull out the pinout, which is what we had before. So it can be a GPIO, and it can be a timer, and it can be an interrupt controller, and it can do handshake parallel transfers, and it can generate a timer, and it has a serial to parallel, and it is entirely possible that I forgot a few usage. So it's a really interesting device, a lot of functionality, lives up to its name. And that's what we're going to try and emulate. So what that means is we'll write code that the emulated 6502 can interface with that behaves like the 6522. Okay, so in order to do that, we need to understand the external interfaces the 6522 has. And this is how it works. Let's just turn on annotations as soon as I found how. Tools, annotations, okay. So some of the pins here are CPU facing, and some of them are outside or interface facing. So if we look at, roughly speaking, the right side of the chip, excluding these two, CA1 and CA2, are CPU facing. So RS0 through RS3 are connected to usually to the lowest 4 bits of the address bus of the CPU. D0 through D7 are 8 bits that are the data bus. And then chip selects and 1 and chip select 2 not are usually derived from the address bus to select when the chip is active on the CPU facing side of it. And then there's the read write, which is also part. So this one, this one, this one, and all of these are all CPU facing. In addition to that, Phi2 is the clock that the chip needs, and it's pretty much assumed that it's the same clock that the CPU is using. So we can count this one as also CPU facing. Reset is part of the whole system reset. So again, we kind of assume it's part of the CPU domain. And last but not least, IRQ is also CPU facing, but in the other direction. So all of those are initiated by the CPU and driven into the 6522. And the IRQ is in the opposite direction. The 6522 drives it, and the CPU is the recipient. So all of those pins are CPU facing. What we have on the other side, the interface facing, we have 8 bits of data, and then 8 bits more of data. So that's port A and port B. And then we have control A 1 and 2 and control B 1 and 2. So, and these are, like I said, these are loaded with functionality. There are various ways we can activate them. So let's start let's start at the beginning. Okay, let's start with the infrastructure. Just a second. Okay. So we have our project. Not yet. Okay. We have our project. So that's the SAR 1541. I should remind you that the project is also available on GitHub at CompuSAR at SAR 1541. So everything I do is available here, and it's up to date to where we are right now. Okay. What I did do change during the hiatus, longer than expected hiatus I took, is I switched the build system to CMake so that things will work better. So the first thing we want to do is we want to add another source file, which is we'll call it mos6522.cpp, whatever. And now we want to actually create that file. So we want the H, where as usual we do the pragma thing, and then a class mos6522. Let's do capital letter because that's a convention. And we also want the CPP file, which of course starts by including okay, let's see. Let's make sure that compiles. Great. One more thing. We want to git add these files so we can track changes to them. Makes things easier later on. Okay. What do we actually want here? So what we'll do is we'll start going over the datasheet, see what functionality is needed. But sorry, before that, we need to decide how we implement the CPU facing side and how we implement the outside, the interface facing side. So the CPU facing side will implement pretty much the same way we implemented the CPU. We'll have the CPU facing side are requests, right? They do read this register or write this register, basically. So we'll implement those directly. We'll have a uint8 read, and then we'll have it's actually only 4 bits, but still a uint8t. And we'll actually use address, and we'll trim it to the lower 4 bits. Register select. So that's one. You'll notice I did not mark this const. The reason being, there are some registers that reading them changes the state of the chip. So it's not const, it changes the state. And then we have write, which goes address and uint8 data. And obviously that's not const either. So those are the CPU facing functionality. We also need interface facing functionality, which we'll handle in a moment. But we also need a main function. Because since we have a timer here, and we have a clock, and we have things that are not a trigger of any external signal, but of the time passing, we need a main function here. So we'll have a execute or main, whatever. So those are our main functions. And then, like I said, um, we want something which is like the way we did with the 6502, where we had a bus defined, and then we got, in the constructor, we got a reference to that bus that had virtual function that implement what actually reading or writing looks like. So we want something similar here. So we'll have another file called MOS6522 interface, which will have class MOS6522 interface. Very original name, I know. Which will have virtual destructor, because it's virtual. And it will have various virtual functions which we'll define later. What we will need, however, is to include that. And we'll want a constructor that accepts that. So just like we did here, we'll have MOS6522 that gets MOS6522 interface a pin out, and it basically just stores it. So that's the interface is pin out, and that's okay. So those pretty much are the preparations. Now let's do begin the actual implementation. So we'll begin with MOS6522 main. My kids are fighting in the background. Please do ignore. Okay, main is an infinite loop. So while true, and we will do something. And then what we will also need is something that will mean that the time passed. So we'll add in something else here, which we'll define later, which is a system clock. And I'll handle what that is later. System clock. And just like this, go okay. So essentially, while true, system clock tick. And we'll handle what that means some other time. We'll just do class system clock so that it will compile. I'll comment this out for now. Okay. It's time to actually begin implementation. And what we'll do is we'll pick the data sheet. Okay, so what I have here are 4 data sheets for 4 different manufacturers of the 6522. So I have, this is by Synertech, this is by MOS, this is by Western Design Center, and this is and this is by Rockwell. So we have 4 manufacturers, and essentially the Rockwell datasheet is pretty much useless. It's also, it doesn't have anything useful. The Cinetech datasheet is much more useful, especially with the addendum. The Western Design Center is somewhere in the middle. And the MOS one is very detailed and very accurate, but not very clear. So we'll try and use that. And again, please ignore the noise from my kids. Okay. So what we have here, that's the main thing. That's what we came here to see. Those are the register select pins, so 0 through 15, and what register they actually select. But of course, that doesn't help us much. So if we scroll a little down, that's the processor interface. We don't care about that because we're not actually implementing that. We replace that with these two functions. And then we start with the peripheral interface, finally. So the first thing we document here, here are the operation. So the first thing we have are the GPIO pins. What does GPIO mean? GPIO means general purpose input output. So if we, let's take the, no, that's the 6502. Let's take the Western Design Center. Let's take the Cinetech. Somewhere in here they'll have the pinout. No, they will not. Rockwell, fine. So if we look, we have 2 ports, so port A and port B, and each of those port A and B can be set directly with a value. So they can be either input or output, and if they're output, they can be either 0 or 1. So that's what general purpose input output means. So that's the GPIO interface. Now, if we go over what the registers mean, it goes like this. Port registers, handshake control. Here we go. No, we don't want the timer. Yeah, I think for these we'll take actually the Western Design Center data sheet because it's clearer. So, timing, caveats, registers. Okay, so first of all, we have a register called ORB and IRB. It starts with B for some reason. Yeah, because register number 0, so all of the register select lines are low. Selects ORB, which is the output register B, and that if we write, that's what we're getting. And IRB, the input register B, if we read, that's what we're getting. So if we're looking at the pins, and the pin is in output mode, what it outputs is ORB. Sorry, here, ORB. If it's in input mode, whatever it's receiving, we can read by reading IRB. Now, typically, we don't need a register for the input, but since this is an emulation, we actually do. So we need an 8-bit register for ORB and IRB, and we will initialize both to 0. Okay. Now, let's implement the read. So, uint 8t register select. So what we need here essentially is we need to select which register we're accessing. So we go switch register select, and we only need the bottom 4 bits. So 0F. And then if we are selecting register 0, then we need, since we're in a read mode, we need to return IRB. And then if we implement the write, we do pretty much the same thing. We ask which register we're writing to. But now things are a little more complicated, because we need to, so first of all, we need to write the value we got to a ORB. So that's simple enough. We go ORB equals data. But that's not enough, because we also have the output pins that we need to control. And like I said, those are controlled through the interface class, which we still haven't defined. So what we need here now is to say, okay, interface pin out, and we need to say, okay, so pin out B. And now we need to say the value for the pins, but we don't need to update all the pins. We only update the pins that are registered as output. And that's actually handled by the next register, which is register 2, the data direction register for B. So first of all, let's define that register. So we need DDRB. And if we write to a register 2, we do DDRB equals data. So what we really need, and that may also update the output pins, right? So what we'll do here is do update output 1. No, update output B. And this way we can do here update output B. So if we update the output register or we update the data direction register, we update what pins are actually set to 1. Okay, that's simple enough. And now we have the matching pair, which is register select 1 and 3, which goes ORA IRA and data direction A. So we'll just copy what we have. And we're switching B to A. And the same goes here. ORA, A, and break does not become a rake. And the same goes here. A, Okay. How does this work? They actually have an explanation, but we'll do it ourselves. So, void update output A and B. Here's the rule. If DDR is 0 for a bit, that means the corresponding pin is an input pin, which means that we do not need to output what's in output register for that pin. So what we need to do essentially is OR the output register with the data direction register. So we need ORA or DDRA. And we want to set the output out pins A to that value. And output B is pretty much the same. Okay. And that essentially is the GPIO functionality. So the first 4 registers handle, that's the GP output functionality. We still need to handle the input functionality. Okay. So the input functionality goes like this. By the way, no, I think I got it wrong. So let's just look at the when reading right output level. No, okay, so that was right. Okay. Okay. So the input functionality, what we need is for a way for an external entity what we need is for an external entity to be able to update the input values that we need to see here. So how do we do that? What we need to do is to get, okay, these are the peripheral interface, and we need to allow updating a single bit. So void set input bit, and we need a port, which will provide an enum for. And we want the bit number, and we want the value. So let's implement that. Okay, so first we need to select which one we're after by selecting the port. So we go, the port is the input register, so we go uint 8t reference in, and that equals port A, then it's in IRA, otherwise it's IRB. Next, we need to see whether we're setting a bit or clearing a bit. So if value, we're setting a bit, else we're clearing. If we're setting a bit, we do in or, so that will set the relevant bit, 1 shifted left by bit. Otherwise, we go in and, so that will clear a bit, the opposite of 1 bit. Okay. And now, if we want to read a register, all we need to do is exactly what we did here. So if we just read the input register, and it will give us the most up-to-date value. As for the data direction, reading it just returns the value we last stored in it, so nothing very special here. Okay. And that pretty much, we haven't compiled it, which it won't compile because this needs a definition. Let's add it so that it can compile. Uint 8 obviously isn't defined. Where did we define ADDR? At bus.h. Okay, so we'll include bus.h. And it complains that interface doesn't have out pins A, which is a fair complaint. So out pins A, void pins A uint 8t data. And that's of course virtual. And the same goes for B. Control reaches of non-void on line 20. Yeah, that's a fair statement, but not relevant yet. Okay, so everything compiles, doesn't run, but that's fine. We'll just, that's a good time to lock it all in place. .522 GPIO. Committed. Okay. Next, we have the timers. Let's switch to the MOS. Timer. timer 1. Timer 1 has two operation modes. One is a 16-bit countdown timer, which means we load it with a 16-bit value, which requires two bus operations because our bus is 8-bit. And then it counts down until it reaches 0, at which point it sets an interrupt, which doesn't exactly mean setting an interrupt. Okay, so there are several things we need here. First thing we need is a 16-bit counter, of course. So let's start with that. So those are uint 16t timer 1, and we also need timer 1 latch. I will initialize both to 0. Here's the thing. In most cases, we do not actually set the value in the timer. There are some cases where we do, but in most cases we don't. What we do is we set the value in some intermediate place called the latch, and then when we hit go, these values are copied into the timer. So how does that work? If we are at low, high, low, low, that's 4. Okay, so if we are writing to register select 4, so we are writing to register select 4. What happens is we are writing into the low order latch for timer 1. So what we're doing is we're doing timer 1 latch. Actually, let's do it like this. uint 8t timer 1 latch low, timer 1 latch high. So timer latch low equals data. And that's it. We do nothing else. Now you'll notice that while that happens, the clock continues to tick and the timer continues to update. But that's fine. Next, if we write to low, high, which is 5, what happens is that we write the value into the high order latch. So that's step 1. Timer 1 latch high equals data. But then we also write it into the high order counter. So, and we also transfer the low order latch into the low order counter. So we do timer 1 equals timer latch high shifted left by 8 or timer 1 low. So we write the value into the high part of the latch, and then we shift the entire 16-bit latch into the timer. And we reset the interrupt flag. Now, yeah, okay. uint 8t interrupt equals 0. So we want interrupt and equals, and now we need static const expr uint unsigned, and now and we need the t1 interrupt equals, I don't remember how much, we'll fill that in later. For now, let's assume it's 0. So we go we reset the bit that says timer 1 has an active reset. So those are the 3 operations that happen if we write to register 5. And then if we write to register 6, we just write to the low order latch. So timer 1 latch low equals data. So you'll notice that writing to 6 and writing to 4 actually does the same thing, which is true, but reading does not. Reading does something different. We can actually do this. And writing to register 7, write the high order latch and reset the interrupt flag. So case 7 does this and does this, but does not do this. So that's the writing of the registers. Next, we have reading the registers. So if we are reading from register 4, read the timer 1 low order counter, which is easy enough. So we return timer 1 and the bottom 8 bits of timer 1. If we read from 5, read the high order counter. But also reset the interrupt flag. So let's do reset interrupt, T1 interrupt. Enum class interrupts. Let's make it a bit clearer. Okay. So we need void reset interrupt and set interrupt. Okay, so that's, we were to read from 4, we reset the interrupt and we return the lower 8 bits. If we read from 5, we read the high order counter. So return timer 1 shifted right by 8 bits. Reading from 6 reads the low order latch. So we see here that reading from 6 and reading from 4 aren't the same thing, even though writing to 6 and writing to 4 are the same thing. Return timer 1 latch low. And if we're reading from 7, we return timer latch high. Okay. And now we have the timer one operation modes. And essentially it has four operation modes. So operation mode 0 is generate a single timeout interrupt each time T1 is loaded. Operation mode 1 means generate continuous interrupts. 2, generate single interrupt and output pulse on PB7. We'll get to what that means in a second. And 3, generate continuous interrupts and a square wave out on PB7. So back at the beginning of this session, I said that the versatile interface adapter is versatile. And I pointed out that it has various timer uses. And it went like this. It can count time, which is what this interrupt is all about. So we load it with a value. It counts down. When it reaches 0, it gives us an interrupt, and we know that it has finished. And then it has a mode of repeated interrupts, which means that it counts down. It gives us an interrupt, but immediately it loads the value and counting down again. That's why we have the latch value and the timer value. And then we have the same thing, except we count down once or we count down repeatedly. But while we do that, we keep outputting a bit on the B port pin 7, where we output a clock there, which is a division of our input clock. So we can use our input clock to generate an output clock, whatever value we want, pretty much. So these are the operating modes. Just a second. Okay. So what's ACR7 and ACR6? These are set using a different register. So we have, I don't remember right now which. Let's just check with ACR7. Timer 2 operation, shift register operation. Here we go. So shift register and auxiliary control. So that's 0A. So we have a register which we access by accessing offset 0A. And it has a bunch of bits, each doing something. That's called the auxiliary control register. And bit 7 and bit 6 of the auxiliary control register control how timer 1 behaves. So we can see here that we can't, but whatever. So we will add uint 8t aux control reg, and we'll set it to 0. What you'll notice is that we already have more registers in the 6522 than we had in the 6502. We already need more state to see where we currently are in the 6522 than we needed to for the entire 6502 implementation. I just find it funny. And we haven't finished implementing the 6522. So the 6502 is obviously more generic, but the 6522 is a more a complex, directly complex chip, which again I find funny. Okay, so we need to actually implement timer 1, and the place to implement it is here inside the main loop. And what we need to do is this. First of all, we decrement it by 1. So we go timer 1 minus before doing anything else. Now, if timer 1 is 0, then we need to do a bunch of stuff. What stuff? So let's go back to the table that explains what are the different timer 1 modes of operation. And so the first thing we need to do is pick up ACR6 and ACR7, so bit 6 and 7 of the auxiliary control register. Which, okay, just so we can take this off our plate, we go A, return auxiliary control register, and case A, auxiliary control register equals data, just so we know we've implemented it. Okay, so auxiliary control register, if timer 1 equals 0, and then we go switch auxiliary control register shift right by 6 bits. So that will give us the top 2 bits of the auxiliary control register. And now we go, if it's 0, then we're in single timeout interrupt mode. So what we need to do is generate an interrupt if, and this is where it gets kind of icky, if this isn't a wraparound. So it's possible that we've set the latch to say 1,000 cycles. 1,000 cycles have passed. We issued an interrupt, and now we continue decrementing timer 1. This is not a bug. This is what the datasheet says we need to do. Reading timer 1 after an interrupt should return negative values. It allows the CPU to check once it handles the interrupt by how long ago the interrupt took place. But if timer 1 continues to decrement, at some point, 65,536 cycles later to be precise, which isn't a long time, but if we are running at 1 megahertz, that will happen after 65 milliseconds. Timer 1 will get to 0 again. So what we need is a boolean saying timer 1 int armed, and it defaults to false. So we're saying if timer 1 interrupt armed, we set interrupt T1, and timer 1 interrupt arm is false. So we set the interrupt, and we say, but next time don't. Next time don't. So that's for the one shot. If we are in mode 1, which means generate continuous interrupts, then if timer 1, no, we don't care if timer 1 int armed is set or not, because we're in continuous interrupts. So what we are doing is we are set interrupt T1 and timer 1 equals timer 1 latch high shifted right by 8 or timer 1 latch low. So we are resetting the timer for another go. Next, if we are in mode 2. So we need to do the same thing. So essentially, okay, we have two things here. We can check just bit 7. Sorry, we can check just bit 6. So we can go if aux control and so if it's set, then we are in continuous mode. Else we do this. Okay. And now we need to also check bit 7. And this goes like this. So we do not set the interrupt. That we've already handled the case for the interrupt, so we don't care about that. Now we're saying if bit 7 is set, an output pulse on PB7. So PB7, actually I'm not sure how this mode works. I'll have to look it up. I'll do it later. But for this mode, go if timer 1 armed. So we'll do this check before that check. If timer 1 armed, what we need to do is flip bit 7. And again, I haven't checked yet whether that actually appears in the output register. So there are two ways to set PB7. One way is to actually change the bit in output register B, actually change bit 7. And the other way is to say pin PB7 is taken from output register B unless ACR pin 7 is set, in which case it's taken from a different register. And I don't know which of those the 6522 does. I will have to check it on an actual chip. So for now, I'll leave a comment, but for now we'll go ORB XOR ORB XOR I'll just flip the actual bit, and I'll leave a comment saying check whether affects ORB on real chip. So that's timer 1. We have the timing graphs to illustrate exactly what needs to happen. I think we'll stop here. Timer 2 is similar, but not identical. It has different modes. You see it only get affected. It only gets affected. It has a different modes a little. But yeah, I think we'll stop here. Thanks everyone who joined. I hope to see you next week.